Hello and welcome to today's webinar. The topic today will be member and service design of timber components in RFEM 6. My name is Jasmin Hartung. I work at Dlubal Software in the Department of Marketing and Public Relations, and I will be your host today. The presenter today will be Gerhard Rehm, and for your questions, there will be my colleague Markus Baumgartel answering them. But my colleagues can now briefly introduce themselves a bit further.
Yeah, hello, my name is Gerhard Rehm. I'm the presenter today, and I'm happy to present the timber add-on today. And yeah, let's see. Thank you.
Hello, my name is Markus Baumgartel. I'm responsible for customer support and frequently asked questions on our website. And today I will help my colleague Gerhard to answer your questions during this webinar. Okay.
Okay, thank you very much. Now we can turn off the webcam so that the viewers can see the whole screen. Okay, great. Before we start with the presentation, I'd like to mention that you have the possibility to, of course, ask us questions. Therefore, you can use the control panel on the right side of your screen, as you can see here. If you want to ask a question, you can just put it in here, press on send, and then we will try to answer all of them during the webinar. If there are too many questions for us to answer right now, we will send you an answer briefly after the webinar. And if you just want to watch the webinar for now and have any questions later on, then you can always send them to info@dlubal.com and we will send you a response. Okay, I will now hand over the screen to my colleague Gerhard and we can start.
Yes, okay, thank you. And today's topic is modeling a timber floor slab considering different variants. So here on the right-hand side, or you see the different variants in one picture. We will not do the same today, but of course, at the whole slab, we will use the same approach. That's clear. We compare it with wooden beams and glulam beams and CLT. During the presentation, I will come up with a few new features which are available in timber design. So it's not an own blog, it's just step-by-step information. Okay, so we will design the floor and afterwards we will transfer the load into a submodel or another model. And at the end, we will have an outlook on further development and new features. Okay, to get an overview, I show you the model in CAD-work. So this is a single family house and let's check the basement here. It's made of, or the system is timber frame walls, and here we see the floor. So we see the bearing beams and floor beams or ceiling beams. And as you can see, the ceiling beams as well on the real image, they are supported on this bearing beams here, on the down beams, but the architect or the building constructor, they want to have the bottom edge of the beams on the same level. So it was decided to lift the beam a bit. You can see it here. So the ceiling beams are connected via dovetail connection, and the bearing beam will be a bit inside the ceiling structure. Otherwise, we would get to less stiffness, and it was decided to lift this a bit up. And maybe not so good for acoustic reasons, but the building constructor decided to have it bottom to bottom for floor and bearing beam here, or for this downstem beam or flush beam, however you call it. Okay, you can export the file via the IFC interface, for example, or via the DXF interface. We will be able to export it also on the old way, what we had in RFEM 5 via the DSTV interface. This will be available soon. but yeah, because of time reasons, I will not show you the import or export today. I start directly with a finished model. If you are interested in the import export via the IFC interface, maybe it's worth to watch the German webinar, which was done on Tuesday, but because of time, I decided to skip this part in the English one. If you're interested in, just check the German one. And even when you don't understand the language, you will understand the pictures and how it is done. Okay, so we have imported all members already, and we have, or I have assigned the hinges. So we have 3 one-span beams. We have here our bearing beams. We have here the staircase. So maybe let's go back here. So there's the staircase here. And that's why we have this cantilevers here. And yeah, actually we have everything finished. I decided to create just one support with a few springs to avoid that the beam rotate around their own axis. So yeah, it keeps it simple. Okay, so I will switch to the top view. And I have created already 3 load cases. So load case 1, load case 2, load case 3. And we will apply the loads right now. So there are 2 ways, or actually 3 ways, to apply the loads here on these floor beams or on the ceiling beams. The first one is the manual member load. The second one is the member load from an area load. And this is what I show you today. We will not use it. I will delete it afterwards, but there's a new feature inside and I want to show it to you. Okay, we apply here 2.5 kilonewton and I will select the geometry by picking these nodes. And we simply click OK. And maybe let's start with this view. So this is our area load. And when we display it separately, we will see how the loads are distributed to the beams. Yeah. So let's focus, for example, on this node here. You can see there is this linear distribution and there's this node load. And sometimes it was hard to understand how the distribution works, yeah, or from this tributary area this loads comes from, yeah. And here in the display navigator under load wizard, you will find this option now to display the distribution areas. So when you activate it, I will deactivate the nodal supports here for a better overview. And when you select the node, you will get these colors here. And now you can perfectly see the tributary area. And you see, okay, perfect. This nodal load or this nodal force comes from this area. So in the background, or actually you see now these Voronoi cells, which are used here for this approach. Yeah, and this, I guess, it's really handy because of a better overview and the understanding of the approach. Yeah, of course, if I go to the load again and say, please remove all beams which are parallel to the bearing beams, then we get our typical distribution, what I want to use here now. Yeah, and also the Voronoi cells. Okay, but as I mentioned, we don't want to use it here. That's why I delete it. Because we want to use the surface, the load transfer surface. Means we will create a new surface by selecting boundary lines, and the stiffness type I will switch over to load transfer. So now I need to select all these lines, these boundary lines. Okay, let's have a look on the local axis system. Here we go. Reverse local axis system. Yeah, I want to have it downwards. I was a bit confused. Okay. Yeah, we see, okay, the local y-axis goes parallel to the global y-axis, means perpendicular to the ceiling beams. And yeah, that's why I will switch over now in the load transfer to Y direction. I want to distribute it via the Y direction, yeah, to all members. And as we can see here, we have nodes which will be also loaded. And these nodes are located exactly here on this location and this location, same as we had before in this load wizard. That's why I don't want to use it. I copied these numbers and insert it directly here. Otherwise, we would get small nodes here, small node loads on these locations, and I want to avoid it. Okay. We can switch off again the local access system. And now let's load it. We will apply a self-weight, additional self-weight of 2.5 kilonewton per square meters. That's from the ceiling structure. Okay. And when we right-click the surface, we can display it also separately, same like for the load wizard. Okay, that's actually exactly what I want to see. But when we remember there was the staircase here, and on the left and on the right side, of course, we consider only 50% of the load because the surface is only modeled until this location. Of course, I can extend the surface by another 50% of the spacing, but in this case, I show you some other new function called load distribution factor. I activate these factors, and now I can assign to this member and also to this member, please consider the load by factor 2. And now when we check it, so it's 0.9. When I hit the OK button, it becomes 1.8 again. Okay, that's self-weight. Let's switch over to impost load. Here, I want to consider it per span because afterwards we want to check continuous floor. Here we have 3 times a one span beam, and afterwards it will be a continuous beam. That's why I directly loaded with 2 load cases on the first and on the third span, and the load case 3 in this case is for the intermediate span. Okay, so in this case I cannot use surface load, of course, because the surface is not divided here on these lines, but I can use free loads, in this case free rectangular loads. So it's for surface 1. Oops. And I select the area from here to here. I click apply and next. Of course, we need a magnitude, in this case, 2 kilonewton per square meters. And again, for the third span, to zoom in a bit, here we go. And click OK. And we will see the distributed loads. All right, switch over to load case 3. And in this case, we have this corner, so we cannot use the rectangular load. We will use the free polygon load. Okay, I will select here the corners. Also 2 kilonewton per square meters on surface 1. Yeah, and that's it. Okay. So before we start designing the design, before we start to design the floor, we will check, because of plausibility reasons, if everything is correct. So I run the analysis now only for self-weight 1, and let's check the deformation, moment distributions, and so on. Okay, I'm not interested in the nodes and the support reactions. Let's check the deformations first. Maybe, colored, it does not matter. So it looks good, and this is exactly what I expect. Let's switch over to internal forces. So we should have no normal forces inside, no shear forces in Y direction, of course, in Z direction. That makes sense. And no torsional moments, that's also good. Bending moments look like for every one span beam, that's okay. Here we have our hugging moment, which is also fine on this cantilever. Yeah, Okay, looks good so far, and now we can start to think about the design. Okay, let's check, for example, this floor beam first. So when we come to design, we need to think about, okay, what about stability? Is there any problem with stability? I mean, for this floor, of course not. We have no normal forces. We have really, slender or, non-slender cross sections. So lateral torsional buckling is also not a big deal here. That's why I go to the ultimate config, which are assigned to all members. And I will switch here to do not perform stability analysis. So then I can get rid of the buckling lengths. Okay, and for serviceability, it detects the reference lengths like for the member length. So in this case, 4.40 m, which is okay. So that means I don't have to do anything for the floor beams, but for the downstand beams and also for these beams here and for the cantilever. Because right now, if I would design it as a member for this beam here, I would get a reference length of 2.18 m, which is of course not wish. We should use a reference length for the SLS design of, in this case, it's 3.44 m. And this we do by combining these two members using a member set. Okay, I want to overtake the design properties. So the design properties are not on the member anymore. They are now on the member set. And when we check the design and deflection tab, we will see now we get a reference length of 3.44 m, which is okay. So we will additionally create member sets for the downstand beams. And in this case, I will create also a member set, 3 member sets, and for this member set and this member set, we will do exactly the same. We activate the design properties. We have a reference length of 2.90 m for one member set and 3.33 m for the other one. Okay. And let's have a look on this beam here. Here, of course, we get really high load, and that's why I also add some design supports. So the reference length is still okay for the serviceability check, but I want to check the bearing area. It means I want to check the compression perpendicular to the grain. So that's why we need to create a design support. So design length is 200 millimeters. And in this case, it's not an inner support, it's an edge support. And the KC90 factor needs to be selected here. In this case, for Dlubal, I select 175. And that's it actually, but I want to mention these two new options, shear reduction and reinforced elements. So the first one is ignoring the shear force in a distance from the support edge, in a distance of member height from the support edge. That means we will use the relevant shear force for the design. So this is nothing else than we have really high compression perpendicular to the grain inside. That means that increases our shear strength. Yeah, and that's why it's okay to, of course, only when the load comes on from top side. Yeah, in this case, of course, I cannot use it because the load comes actually from the bottom side. But if the load comes from the top side, it causes some compression perpendicular inside the beam, and this will help to increase the shear strength. This is mentioned in some national annexes like German one, Austrian one, and I guess in the Finnish one, I'm not 100% sure. Maybe much more annexes, I'm not sure. Okay, and the second option is the reinforced elements. Means we can reinforce the bearing area by some fully threaded screws. So in this case, you can define your screw with your parameters. There is no library so far. We are not sure about a library because it's really time consuming with all of the screw producers. I mean, we started with inserting everything manually, but I guess it's not a big deal. We know the screw lengths, the yield strength more normally is around 1000 Newton per square millimeters, and the other values for tensile strength and withdrawal strength is in the approval of the screw producers. So actually everything is not a big deal. Okay, and then the support pressure will be bared by the screws and not by contact via timber, where timber is actually really weak compared to parallel to the grain. Okay, oh, I need to create it, of course. So 200 millimeters and 175, and also at the other side. Okay, that's it. Yeah, we need to do the same for the cantilevers here. Oops. So when we check the lengths, the reference lengths, it would be considered with 5.20 meters from member start through member end. Of course, this is not a wish behavior. We want to check this here with a reference length for cantilevers and this for beams. So in this case, we need to create segments, and segments can be created by using some design supports. In this case, I don't want to check compression perpendicular to the grain. That's why I'll switch to direct support, to indirect support. So it means I will switch off direct support option here. Then no design is done for compression perpendicular to the grain, and it detects here this tiny node, and I want to apply it to the intermediate node also, of course, not at member set start or member start. Yeah, and now we will see when we check, for example, only C direction, there's one segment for the cantilever with 126 and another segment with 3.94 meters. And these reference lengths are used for the design. And since there is no support here, the program automatically detects that this must be a cantilever. Okay, good. I think so far that's it. We can run the analysis. Oh, yeah, that was the wrong button. I clicked analysis for load case 1 only and not for all. Oh, maybe good to see that I want to explain something more about the timber design. So we will switch to our timber design. We want to check ULS and SLS. In this case, I guess I have chosen the German annex. I'm not 100% sure now. That's why I check it again. Yeah, it's the German annex, but of course, you know, you can select your annex according to your country. Okay, so in this case, we check ULS, SLS. We have characteristic, quasi-permanent, and a mixture of characteristic, deformation, and the creep parts of the quasi-permanent one. Objects to design, okay, all member sets and all members, but you see we will get some invalid members. When we select it, we will directly see the invalid members are members without design properties because the design property is here in the member set. So to get rid of any warning message at the end of the calculation, I insert here only the list of all members, here of all member sets, and of course surface, that's a load transfer surface, cannot be designed. That's why I switched it off here as well. Materials, okay, it was overtaken here, GL24 for the glulam beams and the C24 for the ceiling beams. Okay, when we go to sections, we should think about the sections here. Here, this is this inversed T-beam. And when we check it in the model, I also use, wait a minute, I create a visibility. I also use this, this inverse T-beam here. But when we think about the connection, we have these notches here coming from the dovetails. And of course, in this case, better to not consider it for the ULS design. For SLS, it's not a big deal because it's not reducing the stiffness, or it is reducing the stiffness, but it's not worth to talk about because the influence is so small. But for ULS, of course, the influence is big, yeah. And in this case, we need to reduce it. And that's why I will directly use here an rectangle section, which is here 18 by 400. Yeah, so this is from here, from this to this edge. And this we can directly use here by using the option use other section for design. So for the left side, it was this one, 24 by 24. And this one is, I guess, 180 millimeter on the top side. Yeah, it doesn't matter. I guess it's the case. Yeah, 180. Okay, so we click here and then we will replace the 240, the width, 290. And here I will also use 180 by 400. Okay, and now we have considered the notches as well, and we can be sure that yeah, the ULS check is correct. Okay, then let's start the ULS check and the SLS check, of course. Okay, we get the results for our load combinations. Let's cancel the view, and now we see, oh, maybe I forgot something. Wait a minute, please. I forgot to assign a config to the member sets. Of course, member sets should have also a ULS config. Otherwise, only a serviceability design check is done. And this is what we don't want to do. All right, so sorry, I need to run the timber analysis again. Of course, not the internal forces, but the timber analysis. Okay, and we see here, our ratio graphically. We see here on the bottom in the table directly, okay, there is one beam which causes some problems. Maybe let's start with the ceiling beams. Okay, so we will get the maximum ratio of, yeah, let's focus on this span here of 75%. We can check it here separately for ULS, which is around 60% ratio, and for SLS, it's around 75%. Okay, that's what I expect. We only see the ratio here. The ratio is affine to the deformation. That's, yeah, especially here on the cantilever, you see directly the ratio affine to the deformation. That's, yeah, so we can confirm that everything is defined correctly. All right, maybe let's go to the next object. In this case, let's check this T-beam here in -x direction. Okay, and what we see here is we see here a ratio and some jumps. Yeah, of course, the first part from here to here is there is shear governing, and from this point to this point, deformation or bending, and here shear again. But if I'm interested in more detail, I can also switch off here ULS and all checks, and I can check it separately. So for example, I want to check only bending, and I get the ratio only for bending or only for shear. Yeah, it's F into the shear force distribution. So, and also I get the ratio at only one X location because of the support bearing resistance. So when we switch to the input, and we switch to the design ratio on members, and we can see, okay, we have compression perpendicular to the grain. Maybe let's open this design check. And here you can see what is done. You see the whole equation, the whole stuff from the code. We have our support length of 200 millimeter extended by another 30 millimeters. Yeah, so you can follow every value in detail or every intermediate value, which helps you to prove your calculation. Okay, additionally, if you are interested, maybe we can do it in the ULS. You have the option to deactivate the ratio envelope, and then you will get 3 different ratios overlapping each other. So the first one is designed 1200, 01, 04, 05. Yeah, and here you can see which ratio it is from which combination. Okay, let's activate again the max of all design checks, so the envelope. And we can see here we have a small issue because of bending, but especially on this location, we know it's a small glue-lam beam with 240 by 240. And when we know that the reference strength of the EN 14080, the glue-lam standard, is giving us the strength for a reference height of 600 millimeters. So we are far away. That means we can use our KH factor, our size factor, which can be considered here in the ULS config. And here you can activate this KH factor according to Eurocode 3.3, chapter 3. And now we can increase the strength up to 10%, so 24 by 1.1 in this case, because the beam is so small. Okay, now we get a ratio only of 94%, which comes from bending. Let's have a look inside. Okay, and we will see here, this is the KH factor, and 1.1 by 24 equals 26.3. Okay, so actually we have proved the floor, so it's okay according to ULS and deformation. Of course, for floors we need to check vibration. Yeah, that's a big topic, maybe leading or controlling. So for this floor, maybe when we have time at the end, I will show you the vibration design check. If we don't have time, I will refer to our website. Yeah, and here on the website, support and learning, you will find videos, and here videos you can search for vibration. And when you scroll down, you see this video here. And here I show you in detail how you can proceed the vibration check. So maybe let's see what about the time at the end, and then maybe I can show you something as well. If not, I refer to this video. Okay, let's say vibration design is fulfilled, and we call the carpenter, for example, and give them the cross sections. On the next day, they call again. Okay, the architect or the building contractor, they called us, and they want to have maybe not a wooden beam ceiling, maybe they want to have a glue-lam ceiling, or they want to have a cross-laminated timber ceiling. That means for us, okay, we have to redo the whole stuff, but of course we want to spend less time as possible. And how can we proceed in this case? So let's think about glue-lam floors or cross-laminated timber floors. Of course, it would be too uneconomic in this case using one-span beams here. So that means in this case we have to use real downspan beams, which are underneath the beams. So in this case we need to think about the cross-section height, especially we have not so much height in the floor. So when we have at least, let's say, 2.50 meters and the downspan beam has already 400, then only 2.10 meters are left. And of course, this is, less. So in this case, we need to keep it, need to keep the downstream beams so small as possible, So in this case, I want to replace these beams here by, in this case, also timber beams. Of course, you can use steel I-beams as well. That's also possible. But I replace here my sections. Let's start with the left one, 24 by 24. Or let's start with the right one. And here I want to replace it, let's say, by 200 by 360. And now we come to also a relative new feature, is about the LVL design. So now we are able to design also LVL materials. So I guess the most famous producer are listed here: Pohlmeier with Baubuche, Onkerto, Steico, Stora Enso. And the advantage is it's not only for beams, it's also prepared for surface design. So all values, maybe we can select Cato Q panel, because all values are available for this material. And you can see all values for stiffness and also for the strengths are available, and we can do a full design. In this case, we select the Baubuche GL75 beam and we click OK. And now we have to think about, okay, what about the lamellas? Are the lamellas orientated flatwise or edgewise now? So let's go back to the material again. And here we see we use an isotropic linear elastic material model. In this case, we use a flatwise orientation of the lamellas. Means like this. So this is flatwise. Of course, if we want to use it edgewise, we can flip the member by 90 degrees. This would be an option. But much better now, we have new material models in RFEM 6 called isotropic timber or orthotropic timber. So when we select isotropic timber and switch to the next tab, we can see, okay, we can switch between parallel and perpendicular and flatwise and edgewise. For Baubuche, there's not much big difference. Only the shear modulus will change when I switch to edgewise. But when we think about OSB materials, for example, of course, they have different stiffness in different directions. And that's actually why this material model was made for. In the past, we had always the problem, in the past, I mean with RFEM 5, we had to decide if the material is wall stressed or plate stressed. And now we can have everything within one material model. So here you can see we have wall stress immoduluses and in both directions and plate stress immodulus in both directions. The beam, the glulam beam or the Baubuche GL75 beam can be used only as a beam. We cannot use it in perpendicular direction. That's why we have 0 values here. Okay, so let's switch this back to isotropic timber, in this case parallel and flatwise. Okay, and we will do the same for cross section number 1. We will switch over the material to Baubuche. Okay, and the floor beams, of course, needs to be changed as well. For a glulam, ceiling, normally we have elements like 60 centimeters or 62 centimeters. In this case, the distance here is around, I guess, 72 centimeters. So for simplification now, I simply switch the floor, the beam width to 720 millimeters and the height, let's try 120 millimeters. And also we switch to GL24. Don't matter about the orientation here of the lamellas. This is just a graphical issue. Okay, when we switch on the rendering, we see, okay, the width fits nearly perfectly here. Maybe not here. The load transfer surface is coming, is visible as well, but I mean, it is okay. It's a small error, but not relevant to mention. Okay, and of course the continuous effect is a topic. So in this case, we will create a new member end hinge. So in this case, we create a so-called scissor hinge for all degrees of freedom, or for all rotational degrees of freedom. And this scissor option causes the effect that no moments are transferred to our downstand beams. And now I select the option assign to members graphically. And when I select it on the right side and here on the left side, maybe here and here on the left side, and this one, and on the right side, we select OK. And now we have assigned this support, this member hinge to the continuous members. Of course, here we have no additional member. We can, oh no, we don't need it. Wait, yeah, we can delete. We can delete it because it's a continuous beam, and we have. Come on, I will switch off the nodal supports. We can select the hinge and delete the hinge manually. Okay, and also here on the bottom we don't need hinges. No, I don't want to select the member. Yeah, the hinge. Okay, and here it seems I have forgotten the hinge on member start. Okay, looks good, looks good. Let's double check it again. Yellow, yeah, check all the yellow colors. Okay, looks good so far. So that's it actually. We have to find everything. So we can run the calculation again. So that's the easiest way to switch from a floor beam, actually from a wooden beam ceiling to a glulam ceiling. So of course we need to recalculate the internal forces. And then we design the members. Okay, so let's check. There is, yeah, okay, in this case, the cantilever, because of the high load here, the cantilevers will be deformed upwards here, and that's why we get this ratio. In this case, I would say I'm not interested in this ratio. You can deactivate the design check here by setting this checkbox to inactive. All right, but we don't care about, let's check. We have, for the glulam, we have a ULS check of, it's this one, of around 36% ratio. And for SLS, we have around 70%, 68, 69%. Okay, so, and let's check also our glulam beams, or our Baubuche beams, sorry. It was section number 1 and 3. Okay, so we have ratio for SLS of 69 and 62, and ULS, yeah, extremely small. So maybe worth to talk about to change it to 320 millimeters. So now we have 200 by 360. Then yeah, we can change it to 320, but that's okay for now. Okay, so we remember the ratio. It was around 38 for ULS and 68 for SLS. Okay, but of course, in case you come from the scratch, you don't want to model this maybe as a girder. Maybe you want to model it directly with surfaces, and this is also possible. In this case, we will select our members, our floor members, or maybe we can only hit this button and right click the member, because we don't need it, because I want to consider now the stiffness via a surface. So that's why I go to edit, and I will switch the beam type now to result beam. So this result beam will not bring us additional stiffness. It considers only that or actually the result beam is just integrating the results from the surface. Yeah, not only the internal forces, but also the deformation. So I create a result beam really small with a small integration area of 1 millimeter, because to have the deformation that's clear, I need a width, yeah, to get something integrated. Okay, that's all. All right, then we should focus on that this beams should not have any ULS config, because we don't want to check it against ULS. We want to check it against SLS in this case, because the ULS check will be done by the surface. And the reason why I did this, I will explain in a few seconds. Okay. And for the surface, I will switch this to standard. And here we create a new thickness. This thickness will be 120 millimeters. And the material is a GL24, that's correct, but not an isotropic material model, which we cannot use for timber for surfaces and solids. So we create a new one. So I will copy this material number 1, and now I will switch to orthotropic linear elastic, but I can also switch to orthotropic timber. So in case of glulam and softwood, it does not matter which one you use, because it's the same. So when we switch to orthotropic, you will see we will get the same modulus for plate and wall stress. So that's why we can also use this one here. Okay, we see here we have the modulus in X direction and in Y direction, which is EX divided by 30. Okay, it should be material 4. Okay, good. Okay, so now we come to deflection, and that was the reason why I left the beams and converted it to result beams, because here we need to define reference lengths. And since I have defined only one surface, it's hard, yeah, because what is the reference length? And I want to consider the deformed system and not, and not the undeformed system. So to make it more clear, I will create this small sketch. So when this is our floor, and let's say this is our deformation. This is the downstand beam 1, downstand beam 2, and this is the edge. Okay, so what we want to check is we want to check the deformation related to the shifted FE nodes. And this is of course hard for the program to determine. Yeah, I mean, we have options here for undeformed system, which I don't want to use. I want to use the deformed system. We can define a reference plane according to the maximum or minimum point, or a user-defined one. So when we think about if I want to check the deformation here, and I define a user-defined plane, for example, like this, you can imagine what happens to the deformation here. They will be absolutely wrong. Sorry, till here. So that's why it's better in this case to use this downstand beams. In case of rigid supports, it's not a big deal. There's no difference. But in case of the semi-rigid supports, it's better to prove it with result beams. Okay, that is why I switch on the config here, and I will switch off serviceability here. Okay, that's it. Now we will switch over again to objects to design, and in this case I want to design surface number 1. All right. Of course, there's a small error now. When we think about glulam beams, so normally they have a width of 60 centimeters or 62. Of course, they don't transfer moments in Y direction, so perpendicular to the grain. Yeah, and of course we have a small A modulus here. Yeah, so when we check the material again, this was this A modulus 300. So there are a few options now. We can either create a user-defined material and override it by maybe 1 Newton per square millimeters, to have no stiffness in Y direction. That is one option. Of course, the second option would be to create multiple surfaces for each beam, which is really time consuming, and the effort is actually less, or there is no effort. The third option would be to modify the stiffness matrix for the surface. So when we check special objects, structure modification, for example, we can create a structure modification, a new one, where we reduce the stiffness for the stiffness matrix element D22, which is the stiffness in Y direction, and the torsional stiffness in, and the torsional stiffness. So we can set this to a factor of 0.001, for example. But yeah, it's so less, that's why I skip it, and I will not consider it in this case. Okay, maybe worse to save the file. And now we can run the analysis. So in this case, we get member results for ULS, for SLS, and we get the ULS design for the surface. Of course, we need to recalculate all internal forces again, and afterwards we will do the timber design. Okay. We can go on with features with features which will be released in the near future. So the first important one is the fire resistance design for initially protected and unprotected surfaces. So there was always this problem that it was available for members but not for surfaces, and we are close to finish this feature, and we can offer fire design also for surfaces, means also for cross-laminated timber. Just need to click the yes button to recover the file. Oh, not okay. Let's check if everything is available. Oh, fortunately, I saved the file. Where is it? Members, okay. Okay, let's run the analysis again. Hopefully it works now. I have no idea what's going on, but it's working okay. Good. Okay, my first mistake was to not checking the image size. In this case, the default value is used of 0.5 meter. Maybe better to adjust it to 0.25 meters. Okay, and let's run the analysis again. Okay, so maybe focus first on the member design. Of course, yeah, you will see the ratio of the downstand beams, but we don't care about the downstand beams now. We are interested in, oh, sorry, it's in German. Oh my God, sorry, it's in the German interface now. I started the wrong version. Come on. Sorry. sorry. I need to open the English interface, of course. My bad. Yeah, let's forward on this new features list. Yeah, that's a big deal, of course. The fire design is already finished. So when you do a fire design for surfaces, you will get already this information about the charring stuff and so on. And in this example, you can see layer number 5 is burned down completely. The 4th is reduced. And here also for the layer 1 and 2. Additionally, maybe if there is someone from Switzerland, we will add the massive one profiled cross sections soon, and we will extend the design supports for tapers and notches. Yeah, this last point I will explain afterwards. Let's go back to our RFEM. Okay, this is the wrong file. I need to open members. Here we go. So now we lost a few minutes. I'm sorry for that. Okay, so we have to change the image size. 0.25. Okay. And now let's rerun the analysis again. Okay. Okay, so switch on the surface results again, and we will switch over to the SLS ratio. Okay, we'll switch the image off. Okay, so using the surface results. So now we have integrated the results from the surface to this result beam, and we have designed this result beam according to SLS, and the ratio is the same like for the member design. Yeah, so this is what I want to show you. And when we switch on the results for the surface, we hopefully get similar results. So the ratio here was around 38% ratio. So we have nearly the same here on this hogging bending moment, which is controlling in this case. Yeah, so it is up to you if you prefer here using some members or better to create directly a surface. Yeah. Additionally, we can design cross-laminated timber here as well. So in this case, we need to create a new thickness as well. Or maybe it would be nice to support also the lines, because you see here the singularities, because I have not replaced the nodal supports by the line supports. So that's why we get the singularities. So better to use line hinges in this case. But for now, it's good. We lost already a lot of time because of this issue. Okay, so when you want to design a cross-laminated timber, we create a new thickness in this case, and we will switch to layers here. This is only available if the layer add-on is activated in the base data. And here we can directly select our composition, for example, from Binderholz, a 5-layered 120 millimeter, and then we can compare the ratio from the glue lamp to the cross-laminated timber. Okay, I mean, this is maybe not. Well, maybe we can run the analysis. It doesn't matter. So we have replaced it. We can check the orientations again for this surface in X and Y direction. So layer 1, 3, and 5 goes in this direction, and layer 2 and 4 in this direction. So it's okay. Here it's the same because of the bending moment. Of course, the elements are larger. Maybe it's worth to model the surface, to split the model at every, in this case, it's 125 centimeters, and add a line hinge in between. So for simplification, I leave this for now. And we can also compare the result here. But of course, we have to aware of singularities because of these nodal supports, which will be more of interest for the CLT design compared to the glue lamp design. Okay. Of course, the design takes a bit longer than the normal surface because we have much more results. We have 5 layers. We have results on top, bottom, and on the intermediate side. That's why it's why it takes a bit longer. Okay, so let's check the values on surfaces also for the envelope. Okay. So, and here the ratio is, we have here a problem. I'm sure this is because of the rolling shear and this singularity. This needs to be analyzed a bit more detailed. We have no time for that today, but in general, it looks okay with 50% ratio for ULS, and for SLS, we have around 85–90%, which is also okay. Okay, that's actually about this design of the floor. And I told you we will come to this load transfer to other model. We reached the next step in this development. So I want to show you how to transfer the load from this nodal support and this nodal support to the columns. So as we see here, of course, the beams are supported by some columns. And also here we have some installations which needs to be considered maybe, and this needs to be checked. In this case, I have prepared already a model with 2 columns, and now we want to design these columns by overtaking the support reactions from the first file. Okay. We have 3.1. Wait a minute, we will delete a close one. Okay. Sorry. Okay, so to show you what happens when there are no results available in the source file, then of course it should be considered somehow in our new file, and that's why I deleted to show you what's happening. Okay, we have here the 2 columns, and these 2 columns have some loads already from the first story, and now we want to add the loads from these nodes here. We need to switch on the numbering in this case. Nodes with support and numbering. So it's numbering 52 and 51, and we want to apply load from 52 to 2 and from 51 to node number 4. And here we can use the new object called import support reactions. So here we see this model members, which is also connected. I'm not sure if I have did I saved it? Hopefully I saved it. Let's see. Members. And here we come to the next tab, objects. So the first option is manually. That means we have to overtake the values manually or connect the values manually. There will be a new option automatically in the future where it detects automatically the nodes based on the location. In this case, I have modeled it independently on the location, so therefore I have to connect it manually either way. Okay, so we deactivate here all nodes and we add node number 52 and 51. And here we want to have 2 and 4. Loading, we can overtake the loads from multiple load cases. So we have here 2 load cases, means we have actually 3 load cases. And we will add this load from load case 3 also to load case 2. So we see we can select the direction, only forces in Z direction or Y or X, and also the rotational degrees of freedom can be overtaken. Okay, I click the OK button and I will see here, okay, there's a question mark because this file knows only it has to look inside this file, but this happens only in case when you calculate the file. Okay, that means I will click the Calculate All button. Now it searches for loads or for support reactions inside the original file, and it will realize there is no result available. It will calculate automatically the load cases and load combinations. And when this is done, we will see here the value will change from a question mark to a real value. And now it starts to calculate the column model. I have set only 2 load cases and only ULS in this case. Okay, so we see this load has the activated option imported support reaction, so we cannot change it. And we can check load case 2, and here we have the 2 load cases. Yeah, and this is how it works to import the support reactions from another file. What happens now when we, for example, add another load to the original model? So I will apply another load here, and you see here the loads are still available. So when does the new file realizes there will be changed, or there are changes in the original, in the source file? That happens when you save the source file. So in this case, when you click the save button again, you will realize directly, okay, maybe I haven't saved it, wait, or maybe that was the automatic save because of this file. Let's try it. No, it's not. That was a copy. Sorry. Yeah, I cannot show it to you now because it was a copy because of this crash. But when I save the file, then this loads becomes question marks automatically. Okay. Yeah, and that's it actually. There is only one missing information what I want to give it to you. So we will consider slip, or actually line hinges in the rigid links in the future. So it's not directly based on Timber add-on, but of course in Timber design we consider a lot of stuff not rigid but semi-rigid, and in the future we will be available. We would be able to connect these 2 members, for example, here with this rigid links. This is just an example. Makes of course no sense here. So when you do this, then you have a rigid connection between these members. And the new option will be that you can add some line hinges here. And then you can consider semi-rigid supports, semi-rigid connections. I guess this will be really helpful, especially for Timber design, because you have always nearly semi-rigid connections. And yeah, of course, you can use line releases to release the members. Sorry, I forgot to add the line releases here for the downstand beams. This is maybe my mistake. I forgot it. Normally, of course, we would release the downstand beams with line releases. But here you can model everything geometrically independent, and then you can connect it with the semi-rigid connection. Okay, then I want to say thank you for listening to my webinar today, and hopefully, yeah, we see us soon. And I will hand over to Jasmine. Bye-bye.
Thank you very much. Okay, before we end this webinar, I'd briefly want to show you that you can book a free appointment with us anytime. If you'd like to know more about the add-ons we used or the RFEM 6 program, you can always just book an appointment with us. It's online, and you can use the link here or use this QR code to access it. And now I will show you where you can find the recording of this webinar on our website. Therefore, you go to News and Events, Webinars. Here you find a list with all the English-speaking upcoming webinars. We have shape optimization of tapered members next week. And if you scroll a bit down, you should find today's webinar. Then you can just click on it. Here will be the recording, You'll also find the PowerPoint presentation here, and we've already attached the used models. I'd like to thank you a lot for your attendance and for participating today. I would like to thank Gerhard again for the amazing presentation, and of course also Markus for answering all the questions. After this webinar, there will be a short survey that it would be nice if you could answer it with 1 being the lowest and 5 the highest rating. I wish you a nice rest of the week and a nice day. Thank you very much. Goodbye.